All right, so today we're going to be talking about modeling inverse variation. And inverse variation is it's the inverse of direct variation, which is how most of your variables have been related during our time together. So when we had linear functions specifically. So when we're looking at direct variation, we're talking about an equation that follows this rule. So we would say y is equal to a multiplied by x. Sometimes the letter k is used there. So if you see k times x, it just means the exact same thing. And in direct variation, the only rule is that a cannot be equal to 0. And a cannot be equal to 0 because if a were equal to 0, then you would be looking at a horizontal line. So there's nothing varying at all there. So basically what's happening in direct variation is this a value is a constant. So as your x value gets bigger, your y value gets bigger, or as your x value gets smaller, your y value gets smaller. So that's what direct variation means there. So when we're looking at the graph, there are two ways that we could see direct variation. So one of them is this right here. And so most of us already know what that would mean about our a value. If we have something that's increasing, it means that our slope is positive. So this would be y is equal to ax when a is greater than 0, right? And then the rule here still actually is, the rule still is that a can't be equal to 0. And then we can also have direct variation that looks like this. And in this is going to be y is equal to ax as when a is less than 0. So here, as my x values are getting bigger in quote unquote value here, these are increasing in value. So that is called direct variation. So right there, direct variation. So inverse variation looks very, very different. So in inverse variation, as one of the quantities is getting bigger, the other quantity is going to be getting smaller. Whereas these change with direct accordance to each other. As one increases, the other increases. Inverse variation is going to be the opposite there. So when we're dealing with inverse variation, we're going to be dealing with the equation y is equal to a divided by x. So think about if this is a constant here, so say that this is 5. If I have, actually, let's say it's 100. That's an easier one to think about. So if I have 100 up here and I'm dividing it by small numbers, I'm going to get big y values. But as the numbers that I'm dividing 100 by get bigger, I'm going to be dividing by 100 by an increasingly larger number. My y values are going to be getting smaller. So that's what inverse variation does. So in inverse variation, there's a couple rules. A still cannot equal 0. And in this one, x also cannot equal 0. And the reason for that is you can't have 0 in the denominator of a fraction. If you try to divide that, you're going to get an error. So what's going to happen is that these are all going to have vertical asymptotes when you graph them at that value of x equals 0. So that vertical line at 0 is going to be a vertical asymptote. And if we remember from vertical asymptotes, it means that the line is going to, or when we talk about asymptotes, that the line gets closer and closer and closer to that value, but it never actually reaches it. So there's two ways that your inverse variation graph can look. So again, our graph is y is equal to a divided by x. And here, if our a value is greater than 0, so if we have a positive a value, it's going to look like this. So you're going to have a graph where you've got one that goes like that, and it shouldn't be curving back like that. It should be going up like that. And then one that goes like this. Then you can also have y is equal to a divided by x, where we have that, and this is when a is less than 0, so this is if your a value is negative, and you're still going to have two of these branches of, that's not supposed to cross, branches of hyperbola there. You're going to have that one there, and you're going to have that one there. And they're supposed to be like symmetrical if you were to reflect them over y equals x, but they're not because this pen is hard to work with. But you get the general gist, I hope. And if you don't, you will, because we're going to keep graphing some of these. So right now we're going to look at some equations, and we're going to determine whether or not, based on the equation, we're looking at direct variation or inverse variation. So remember, in direct and inverse variation, they all have a relationship that says y equals. So in this one, we need to solve for y. So the first thing I'm going to do is I'm going to isolate. I'm going to at least get y out of the denominator of that fraction by multiplying both sides by y. So here my y's are going to cancel out, and I get that y is equal to -4. So now I can divide by x here. So I get y is equal to -4 over x, and that is in the form of inverse variation. So number 2, when we look at this, this is actually, if you look at your choices, it says inverse, direct, or neither. So this is not in the form y equals ax or the form y equals a over x. That we have a constant here. And in direct variation and in inverse variation, we're not going to have constants. So this one here is going to be neither. And number 3, we just need to get it in terms of y, so we can divide each side by x here, and we get that y is equal to 6 divided by x. Well, this is in the form here of inverse variation. And the last one says y equals 8x. Well, that's in the form of y equals a multiplied by x, so this right here is direct variation. So that's how you deal with figuring those out, what type of variation it is, depending on what the equation looks like. So now it's going to give us some information, and it's going to ask us to write an inverse variation equation. So this is asking us to ultimately write an equation in the form of y equals a over x. So basically, we just need an a value. So if we look down here, it says the variables x and y vary inversely. So that's what tells us we need it in this form, and it gives us a y value and an x value. Well, if we look here, y equals a over x, if it gives us an x and a y, we can solve for the value of a. So we're going to say not y equals, we're going to say 5 equals, we don't know what a is, but we know that x is -2. So if I want to isolate that a, I multiply both sides by -2. And I get here that my value of a is equal to -2 times 5. So my a value here is -10. So my inverse variation equation is just y is equal to -10 divided by x. So number 6 is exactly the same here. It tells you that you've got two variables that vary inversely. So that's going to be asking us to write it in this form, y equals a over x, and it gives us a y and it gives us an x. So I know I'm going to set y, which is 9, is equal to a divided by x, which is 5. So to get a by itself, I'm going to multiply both sides by 5. So here I get that a is equal to 5 times 9, which is 45. So when I go to write my inverse variation equation, I get that y is equal to 45 divided by x. All right, so moving on to number 7 and 8 here. These again are exactly the same. It tells us to write an inverse variation equation, so I can just assume that these are different x and y values, and I just need to find an a value. So I know I need to write an equation in the form y equals a over x, so I can pick any set of x and y values from the table and write my equation to find a, because that's the constant that I need to figure out. So here I'd be stating that -10 is equal to a divided by 2. Here I'm going to multiply both sides by 2, and I get that -20 is equal to a. So that gives me the equation y is equal to -20 divided by x. So if you look at this equation here, your a value is always going to be equal to whatever x times y is. Because if you do this number divided by x and get some y value, well, if you do that same number divided by y, you'd get that x value, and that's because x times y is going to equal that a value. So if you look up at our table here, if we're to multiply each of these x, y values together, if you look, each one of these x, y values multiplied together is equal to negative 20, which is your value of a. So right here, our equation, y equals negative 20 divided by x, checks out with our table. So knowing that, most of you actually probably already know what this equation is going to be here, because you know now that you can just multiply your x and your y values. But let's do it mathematically, just to using the formula just to prove it. So that's y equals a divided by x. We can pick any set. Let's pick this set. So I say that 6 is equal to a divided by 2. Again, I multiply both sides by 2. All I'm doing is multiplying x times y to find a, and I sure do get that a is equal to 12. So my equation here is that y is equal to 12 divided by x. So the next thing that we're going to do here is we're going to look at how to graph some of these equations here, or how to graph some inverse functions. So, and what inverse variation does, inverse variation ends up forming an inverse function. So when we go to look at this question here, it says the shape of the graph of an inverse variation equation is equal to y equals a over x. Well, it wants to know what the name of that shape is. And inverse functions are something you'll really get into in Math 3 next year. Inverse functions are what are created by inverse variation relationships. But the graphs, the shape of the graph is called a hyperbola. So hyperbola. It's kind of like hyperbole. It's spelled the same way as hyperbole in language arts class, but it's an A at the end, hyperbola. So that shape where you have those, well, we'll talk more about it. So inside of the hyperbola, there are in each one those two symmetrical parts that were drawn. And those two symmetrical parts are called the branches of hyperbola. So when we go to graph our own here, I'll be really clear about that, what that vocabulary looks like. And then here it says the lines that the hyperbola approaches but doesn't intersect. Anytime they're thinking you hear about a line that something approaches but doesn't intersect, you should be thinking asymptote. And that is absolutely right. They're called asymptotes of hyperbola. All right, so the last thing we're going to do in terms of just informational stuff with this information is to graph a couple of these. So I'm going to give us some x values and some y values, or some x values, we're going to find some y values, then we're going to graph them. So the first thing we want to do is actually get this into inverse variation format. So that would mean that y is equal to 8 divided by x. So I'm going to give you some x values. You make a little table over here. I didn't give myself a lot of room, but I'm going to make it. So the x values that we're going to use here are going to be negative 8, negative 4. I know you don't need a calculator. You have a brain. Negative 2, negative 1, and then 1, 2, 4, 8. And all of these were picked because they're easily divisible by 8. So I'm going to take each one of these x values and I'm going to divide it by 8. Or I'm going to take that value and I'm going to do 8 divided by that value. So the first one is 8 divided by negative 8. Well, that gives me negative 1. Now I've got 8 divided by negative 4. That gives me negative 2. I've got 8 divided by negative 2. That gives me negative 4. 8 divided by negative 1 gives me negative 8. So the only thing that's going to change here is my signs, because now all these are positive. So 8 divided by 1 is 8. 8 divided by 2 is 4. 8 divided by 4 is 2. 8 divided by 8 is 1. So now I have these ordered pairs that I can graph. So I'm gonna pause and graph it so that you don't have to watch me graph all these, but go ahead and graph all of your ordered pairs, please. So right now you should have those points graphed, and we're gonna go ahead and trace down there. So that's one of my branches of hyperbola. I'm gonna be mad that I wrote that right there in a second. And then I'm going to trace down here. And those are my two branches of hyperbola. The entire graph is called a hyperbola. And then your asymptote of hyperbola is here at the x-axis, and that's because x can't be 0. So this whole value, x equals 0, is not part of this equation, so it's never ever going to reach that value. So let's go ahead and look here at number 6. And on number 6, we're looking at another equation that the first thing that we're going to do is we're going to change it into the correct values. So here we're going to have a negative a value. So here we had a positive one. So what's going to shift is where our branches of hyperbola are. So this one is going to be y is equal to negative 6 divided by x. So the x values that we're going to use for this graph are going to be negative 6, negative 3, negative 2, negative 1, and then 1, 2, 3, 6. So those are our x values. Let's go find our y values. Well, negative 6 divided by negative 6 is positive 1. Negative 6 divided by negative 3 is positive 2. Negative 6 divided by negative 2 is positive 3. And negative 6 divided by negative 1 is positive 6. So that's why the location of our branches of hyperbola have shifted. Negative 6 divided by 1 is negative 6. Negative 6 divided by 2 is negative 3. Negative 6 divided by 3 is negative 2. And negative 6 divided by 6 is negative 1. So again, I'm going to pause real quick, and you should pause as well to graph that. And then in just a second, we'll come back and make sure we've got the same graph. All right, so when you finish, your hyperbola graph should look like this. Your branches of hyperbola should have shifted the quadrants that they're in. And the reason for that is because of the negative that was on the a value. So let's go down here and let's do 2 more. These ones are already in the form. So I'm going to give you some x values for each one, and then I'll pause the video. You should pause the video, fill them back in, and then you can play the video again when you are ready to see what they look like. So for this one, we're going to use some x values of negative 5. One of these isn't going to go perfectly, but you can estimate it. Negative 2, negative 1, and then 1, 2, 5. And then for this one, we're going to have our x values are going to be negative 9, negative 3, negative 1, and then 1, 3, and 9. And if you look there, they space the axis out so that you can do that. All right, so go ahead, pause your video, graph these, and then play the video again when you're done graphing them. All right, so 11 and 12 should look like this, kind of. Hopefully yours look better than mine do. But those are the ordered pairs that are graphed there, and then you've got some very bizarre branches of hyperbola drawn there. So hopefully you are a little more successful in drawing those than I was, but hopefully you do now recognize that what these graphs look like. And again, that inverse variation is one gets bigger, the other gets smaller. So right here, your x values are getting bigger, but your y values are getting smaller. And here, your x values are getting functionally, like in their absolute value, they're getting bigger here. And then your y values are getting smaller. So that is, so again, in terms of bigger or smaller here, it's the value of the absolute value of that x value that determines the variation. And the other thing that's important to recognize is that the reason that all of these have this vertical asymptote at the y-axis or along the y-axis is because that's the vertical line at x equals 0. And none of these were allowed to have 0 as an x value because x is by itself there in the denominator. So that's what we've got going on there. And at this point, you're going to go to your Walsh book. There's just a couple examples in there that show us what we can do with this. So we're going to continue along with those. So please grab your Walsh book and go to page 279. All right, so again, this is on page 279 in your Walsh book. And it is basically giving us some more information about inverse variation, some more practice problems that we're going to be doing here. So when you get to this page, just be ready to get going here. All right, so what we're going to do right here is we're going to look at this question using this product rule. And we're also going to look at it kind of another way. So before we look at it using the product rule, we're going to look at it another way. But first I have to figure out why that's why. Okay. So the first thing that we're going to do is kind of thinking about this based on what we did in the last problem already. So we technically already know that if it tells us that you've got something that varies inversely and it gives us an x value and a y value, so we know that we can write that equation there. So what we can do is we could write that y is equal to a over x. We could say that 25 is equal to a over 6. And we know that we would just multiply both sides of the equation here by 6 to get the value of 150. So our equation would be y is equal to 150 divided by x. Well, then we could go in, it asks us to determine the value of y when x is equal to -5. And that basically is just asking us to change x to -5. So that's 150 divided by -5. And it's actually a positive 150. I don't know why I decided to make it negative. And when we solve that out, it tells us right there that y is going to be equal to -30. So based on what we already did there, we actually could have solved this problem, but there's also something called the product rule for inverse variation. And the product rule for inverse variation basically tells us that if we have an XY relationship and we have either X or Y from another relationship, we can solve using this product rule. So it's really saying X1, Y1 equals X2, or X1 times Y1 equals X2 multiplied by Y2. So basically what you can do is you can turn these into ordered pairs. So it says when x is 6, y is 25. So that would be 6, 25, ordered pair, comma. And our second one, it says to determine the value of y when x equals -5. So it would be -5, and this is y2. We don't know what it is. So then we could set up an equation that says that 6 multiplied by 25, because it says x1 times y1, would be equal to x2, which is -5 times y2. And pretty quickly, you're seeing that this is going to turn into that same equation, because this is going to give us 6 times 25, which is still 150. And it's saying 150, is going to be equal to -5 times y2. Well, we know that that means that we need to divide by -5. So ultimately, when we use the equation to determine the value of y here, we get that y2 value is equal again to -30. So this is basically a rule that you can use without having to write the equation. If you know one and the other, you can kind of set up that relationship there. And you notice this is the opposite of a proportion. In a proportion, that you're used to, because proportions are for direct variation, you're used to x over y being equal to x over y. And that's true for direct variation. But we're not doing direct variation, we're doing inverse variation, and that's why x times y is equal to x times y. So let's go into example 2 here. And it's basically just asking us to determine if the constant of variation, well, the constant of variation is A. That's that A value that we had in that last one. And we knew that we could get the A value by multiplying the X and the Y. So 2 times 24, 3 times 16, 4 times 12, 6 times 8. All of those have a product of 48. So we do know that the constant of variation is the same for each ordered pair, so we're good to go there. So it asks us to write the inverse variation equation, which I suppose we can do because we know how to do that. We can use any of those ordered pairs that we want to, but we know that that's going to be, we need y, nope, y is equal to a over x. So I'm going to use 6 and 8. So that would mean that 8 is equal to a over 6. Well, when I multiply by 6, I get that a is equal to 48. So what they're asking us to do now is to follow the calculator steps. We're not going to use our calculator right now. We are going to determine the value of x when y equals 15, and we're going to use that product rule. So what we know is that x1, y1, so multiplying them there, is equal to x2 times y2. So we already know that we're looking for a value of x when y is 15. So I already know that this piece is going to be x2 times 15 because I want the x value when y is 15. Well, to get this first equation, it can be any one of these. And I noticed that any one of these are all just equal to 48. So x times y here, you don't even need to pick an ordered pair. You can just put 48 because when you multiply x times y, it doesn't matter, you're going to get 48 every single time. So now what you need to do is to solve the equation here. You've got that 48 is equal to 15 times x2. So when you divide both sides by 15, you get that x2 would be equal to 3.2, and it absolutely is. So you can go ahead and look at these calculator steps and do this using a calculator, but I don't know why you would want to do that when that is so simple there. So for example 3 here, we're going to look at another piece of information where they tell us that the quantities m and n vary inversely. So it's telling me to use that product rule. So that's the rule where you can multiply the ordered pairs, set them equal. But we know that they're m and n. So let's just say that, oops, oh, wow, I don't even know how that happened. That was like magic. All right, that's not good. I don't know. It has decided that it is. Okay, hold on. I'm going to pause and determine what is occurring. All right, I think everything's okay again. We'll find out in a second. All right, so I have M1 this time multiplied by N1, same thing as X and Y, is going to be equal to M2 multiplied by N2. So if I go look at my ordered pairs, it tells me about an M and an N. So I am going to say, it says when M is equal to 10, N is equal to -4. So here is going to be 10 and -4. And then here it tells me when M is equal to X, N is equal to X minus 13. Oh, wow. Okay. So we know that M is equal to X, so I put X there, and that N is equal to X minus 13. So all we have here is some algebra that we're going to have to solve, but it is going to turn into a quadratic. I hope you recognize that. So I know that 10 times -4 is -40. And here, when I distribute, I get x squared minus 13x. Well, to solve this equation, I want to create an equation that's equal to 0. So I'm going to add 40 to both sides. And I have that 0 is equal to x squared minus 13x plus All right, well, I know I need things that multiply together to give me positive 40, but add to give me negative 13. Don't freak out, they exist. Just think for a second. And they are negative 8 and negative 5. So this is going to give me x minus 8 multiplied by x minus 5. And when I go to set each of those pieces equal to 0, that creates a sign change. So this one is actually going to have two solutions. It is x is going to equal both 8 and also 5. So that's what you have there. And if you were to graph in your calculator, if you put in L1 or Y1, if you put negative 40, and then in Y2, if you put x squared minus 13x and you graphed them, you would find that they intersect at both of those values. All right, so this is one of those situations where they create a word problem for no reason, really. So it's basically telling you that he has 72 square feet of space in his garden, and it tells you it's a rectangle. And so it's basically telling you that you know from Math 2 that length is inversely proportional to the width. And that does make sense because we know that the area is equal to the length times the width, right? And it says the length is inversely proportional to the width. So that would be that the length is equal to the area divided by the width, right? And that makes sense because as the width increases, so if you have only some specific area here, as the width increases, the length has to get smaller. And if the width gets smaller here, then the length has to get bigger. So in area, the length and the width are inversely related. So it tells us that Stuart notices that the lawn in his backyard will restrict how wide his garden can be. That okay. He measures that the restricted width is 4.5 feet, and it wants to know what dimensions his garden can have. Well, we already know that his garden is going to measure 72 square feet. So we already know that the area is 72 square feet, and it already gives us the restricted width, which is 4.5 feet. So we all know that to find our length here, all we need to do is divide, but that fits into this inverse relationship here. Because our area, which is 72, divided by our width, which is 4.5, is going to determine what the length of this garden can be. And when you divide here, you get a value of 16. So we know that the length here on this garden needs to be 16 feet. So our dimensions have to be 4.5 by 16 feet. So I guess what you know now is that if we were to make this value larger, then this value would have to become smaller, which makes sense because when you multiply them together, they still need to give you the same area. And if you make one of the factors bigger and you multiply it by the same number, this one then has to become smaller if it's still going to equal the same product. So we're going to look at the last example here. And example 5 is talks about the relationship between distance and time. So it says that distance is equal to the rate times the time, where distance, D is distance, R is the rate, and T is the time. So it tells you that Taylor drove from her house to the mall with an average speed of 40 miles per hour. So that is going to be a rate. It says the drive took her 26 minutes. So some distance that she traveled from her house to the mall is going to be equal to her rate times her time. Well, it says if the drive going back home took her 32 minutes, it wants to know what was the approximate average speed that she took to get home. Well, right now that might seem confusing, but what we might be forgetting is that we have a situation here where we know for the first one that her distance, right, is equal to her rate times her time. So we know it's going to be equal to her rate, which is 40 miles per hour, times her time, which is 26 minutes. For the second one, some distance took her 32 minutes, but we don't have a rate, but we know that the time is 32 minutes. Well, when we think about these are each set equal to a distance. Well, one of the distances in this first situation measured the distance from her house to the mall, and this one measures the distance from her mall to the house. So if you think about that, what is true, assuming she took the same route, is that the distance is the same. So in order to find this missing value here, we can actually find our, using our inverse product rule, we can find our different rate here because we can set this equation equal to this equation because the distances are equal. Now, if we think about this, we know that at 40 miles per hour, it took her 26 minutes. So now it took her more minutes. So we know that there's an inverse relationship here. So since it took her longer, what can we assume? She's going the same distance and it took her longer. So we can assume that her rate is going to be slower on the way home. But let's go ahead and set this up so we know that the distances are equal to each other. So if the distances are equal to each other, if D is equal to D, well, that tells me that 40 times 26, because that's one of my equations for D, is going to be equal to R multiplied by 32, because that's my other equation for D. And I know those are referring to the exact same distance. So when I go to solve this and I multiply here, I get 1040, and that is going to be equal to 32, and I guess that's times R2, because this would be R1T1, R2T2. So I would divide by 32 here, and I would get that the rate going home would have to be 32.5 miles per hour. And that makes sense that since it took her longer, she's going slower. Her rate should be equal to 32.5. Now, what should be true is when you multiply these together, you should get a distance that is equal to when you multiply these together, and that's because she traveled the same distance on her way to the location that she went as she did on the way home. So just sit tight for a second, or actually, I guess I'm just going to pause this real quick. All right, so your homework for tonight is going to be in your Walsh book. So it's going to start on page 282. And what you might notice is this is the very last thing in your Walsh book, the current Walsh book. So thank goodness those of you that realized that we were at the end of this Walsh book, because I would have been shipping a lot of Walsh books and that would have been really bad. So thank you guys that Friday for remembering and being thoughtful about getting those second Walsh books out. At this point, every single one of you, except for one of you, has the second Walsh book, and that person happens to live near me, so she'll just have to come pick it up. All right, so, and I have an extra one. So right now, your Walsh book should be open to page 282, and you'll see this exact assignment right here. So basically, it's telling you to write an inverse variation equation that really relates x and y and then solve. So for each one of these 1, 2, 3, 4, you're going to need some equation y is equal to a over x. So for each one of these, and then you're also going to have to solve for this missing information here. Same for this one, it asks you to write the inverse variation equation. So all you have to do is write something in the form of y equals a over x. So this is not super challenging. For number 7, they give you this inverse relationship here, and it just asks you to apply it using the information. Just read, figure out which of these numbers is which variable. Again, very simple. This question, if you did the notes, then you should, or if you watched the video notes, then you should have no trouble solving this. Absolutely not, because it's exactly the same. But if you did not watch that, then you are going to have trouble with this. Then for number 9 and 10, it says to solve by graphing or by using a table of values. You can absolutely solve these by graphing. So put that equation in L1, put that equation in L2, graph and solve. For this one, put that equation in L1, put that equation in L2, graph and solve for the intersection. Again, if you don't have a graphing calculator, you can graph them in Desmos and then click the point where they intersect. That's actually probably easier than using your graphing calculator. So again, both of those, you can give me ordered pairs there. And when you find the ordered pairs, you're going to have to round for number 10 for sure. So go ahead and round to the nearest hundredth. So tomorrow I will post the solutions to this homework. And then in Canvas, something will go live that's like it's a practice test. So you're going to open that up to get the file. Then you're also going to open up the place where you can submit it in Canvas. So you'll take that and submit it. And then what'll happen is once all that data comes in, I will look at the data and then any questions that people got wrong, I will make videos of those and then post those because some of them are going to be pretty easy, some of them are going to be harder. But any question that anyone got wrong, I'll make a video and post that. And then what will happen is you'll take another one, and it's almost exactly the same. So, like for instance, if number there's only I know one of them, there's already one that I know that I'm going to do, and that's great. The one on the practice is the exact same thing as the one on the other one. So if you try it, get it wrong, and then you watch the video, think about it, you'll be able to do the next one. So just trust the process here. You're going to be all right. These aren't going to be formal grades, so don't freak out. These are just to so that you know and you're sure that you ascertained what you were supposed to learn during this unit. So again, this is not like some big thing to be scary, but it's just to make sure that you know that you learned what you're supposed to have learned. And then we'll go into unit 4, which is very geometry heavy. So right now, that's that. Always, always, always reach out with any questions. Talk to you guys soon. Bye.